hash tables. So we've learned about different data structures already. We learned about arrays, lists, sorter array, but this is arguably like the best data structure, and that's because operations on this data structure is really fast. So a data structure, we're trying to create a data structure for a mutable collection that implements a set of elements. So these are the, I guess, requirements, you could almost say. A set of elements, let's just say E, and then a set of key value pairs. And then we could name it K and V. And then K is equal to E and V is equal to whatever value that's associated with that specific E. And that's looked up by key. And so this is also just called a map. Oh, we're trying to find a data structure and it has to be mutable. And when we give a key, we need to grab that associated value from it. And basically that's where hash tables come into play. But let's look at other data structures first. And let's look at arrays, linked lists, sorter array. Do you guys have any idea on what the time complexity for searching what specific element is in a unsorted array?
O of n?
Correct, because you would have to iterate through every single index. For removing, what do you guys think? A specific element.
Same thing,
Oh,
O of n.
specific.
Yeah, O of n. And
Because worst case scenario, if you remove it from the front, you have to move everything back, right?
yeah, perfect. Yeah.
Okay.
So, do you guys know what linked lists are?
Yes.
Okay.
Vaguely?
I'll just explain it. So it's like a train, basically, if you think about it. It implements a list, a standard list. You know what list is, right? And linked list is basically another form of that list. So, as you might have guessed, adding is really simple because you can only add at the end of the list, right? Since there's no way to add it, I guess, like in the middle. You could add it, but like
Yeah, you'd have to do a split, and then you'd have to change the nodes, and
Yeah.
you'd have to have a temp value.
Change the pointers on either side of it, right? Or the links on either side.
Yeah, so that would be kind of complex. So for now, let's just say the adding is O of 1, and removing is O of n because you have to go through every list, and then searching is also O of n. And okay, let's do sorter array now. What's the time complexity for sorter arrays?
Log n?
Yeah.
Because that class, Daniel, from Harvard or whatever it was.
Yeah.
Yeah, if you know it's sorted, then you can just start in the middle. If it's bigger, you just look
Yeah.
at next
Yeah,
half.
Yeah, it's
next
half split.
half.
Yeah, so that's like binary search. So all log of n, everything is log of n. So I don't think I have to explain hash tables to you. I mean, not hash table. I don't think I have to explain big O to you guys. I think you guys got it. But basically, a hash table, the operands are all O of 1. So that's why it's so powerful, because everything is O of 1. And that's why for like almost like much of the LeetCode question, we use a hash table, hash set, hash map, because these operations are so cheap and it only takes O of 1 time complexity to do all the searching, containing, adding, removing. So, and these are standard operations. Okay, so yeah, so why don't we try to build a hash table, or like, I guess let's actually just think about these two criteria, and then build I guess a data structure for mutable collection. Okay, keep in mind that we don't know a hash table exists yet, so let's try to build a data structure that implements set of elements E and set of key value pairs looked up by key, and then it has these operations. So one way we can start off with is by using a direct address table, or DAT for short. So we're trying to have some kind of array, I guess, where we have O of 1 add and remove if index is known. So the idea is that we assume, I guess this kind of going to discrete mathematics, but assume injective function f where k maps to a specific index and there's no collisions. No collisions where k1 and k2 are different, but they result in the same value, or same, I guess, same bucket, or like same place where you store the value. So do you guys understand the injective function part? So basically, we assume that we have k1 and k2. These are two different indexes, right? So some kind of function would have to map these k1 into a specific bucket or specific array, space in the array. So k1 and k2 cannot be like this. No collisions where k1 and k2 are different. These are different, but going through this function, they equal the same bucket. Do you kind of understand?
So their value, the F is basically the constraints that we're setting on what the bucket is. So like say, one bucket's even, the other bucket's odd numbers. K1 is 1 and K2 is 2. It forces them into separate buckets versus allowing them both to go into the same bucket.
That's one way you can order the function. Yeah. So, and one way to do this is using a direct address table. So we have I guess infinitely, let's just pretend we have an infinitely amount of space. And let's actually think of a example. Example is houses on a street. And then these houses on the street, let's say, have house numbers 2,940, 2,948, 2,952, and it goes on. What's a cheap function that could map each one of these into their specific buckets? Do you guys have any idea? So these are index. I kind of gave it out, but these are basically our indexes. And basically these map into the corresponding buckets as the numbers itself. 2,940 acts as the index in the array. So that's really cheap, right? Since you don't have to transform this, you don't have to, I guess, make this add or modulo this. And so it's like really cheap. Since you use the index from the street number, from the houses on the street itself. And we know for a fact that there's no duplicate house number, right? So we literally just have 2,940, and at index 2,940, we put that specific house. And we learned about object-oriented programming, so we can also associate this object or whatever with 2,940. We can also have, like, I guess, a color value, red, and 2,948. And maybe this is like blue for some reason. And all of this is empty. So So do you guys kind of understand how this direct address table kind of works?
Yes, so you're basing it off of an index. So that way you just search for the index. If the index exists, then there's a value there. If the index doesn't exist, then it's not in there.
Yeah, perfect. So that would be actually O of 1 lookup. Yeah, so this is actually really, I guess, bad, because while we do have great time complexity, the space complexity is like infinity. Like that's like really bad. So we want something where we can optimize this array size to where we can limit it to certain amount of buckets. Do you guys follow me on that?
So you want to put constraints on the indexes so that way you only have a certain amount of indexes per slot. So that way.
Yeah. You guys got it. Yeah. So let's then think of a cheap function, a hash function, and the idea of this is to limit the array to size m buckets. And then we need some kind of like a cheap function, a hashing almost, to map any k input into some kind of bucket from 0 to m while avoiding collisions. K1 does not equal K2, and then they result in the same bucket. So we use a hash map basically, and what we found out is that the probability, while collisions do occur where you hash and where the inputs are different and they equal to the specific bucket, different input and they equal to the same bucket, what we found out is that through a hash function we can actually limit this through 1 over m. So that's why we used a hash function. So do you guys understand why we use a hash function and why it's so effective? So we do have... yeah.
The probability of it being put in the same bucket erroneously, how do you deal with that?
Oh, yeah. So we'll get to that.
Okay.
Yeah. So let's talk about that hash function specifically. So let's say we have a key that's like really long. So in a direct address table, if we have a key that's like 2940 and then this big number, it's gonna take up too much space, right?
You're gonna need to do some sort of transform to it.
Yeah.
Put it.
So we somehow transform it using a hash, and then somehow put it to a m bucket array. And then I guess maybe this goes to index 95. This transformed into index 95. And then at 95, it's going to have its value stored in there. And hashing, the hash function is kind of like, I guess, you could think of like a magical function that somehow turns a key, whenever you put into it, that specific index. And every time you put that key in, it's going to magically spit out a specific number every single time. And a good hash function makes collisions look random. One way to do it is using just modulo hashing. So pretend we have keys like 4, 2, 3, 2, 2. We modulo by the m buckets to get that specific index. And then any, I guess, and you guys can see like why this kind of works. So any number will be corresponded to an index in that specific area. So let's pretend we have inputs 4, 3, 2, 1. If we have n buckets, like I guess 4 buckets, modulo by the m will perfectly, I guess, put this into each corresponding bucket, right? And I know the confusion here. What if we have 4, 8, 12, 16, right? This is gonna put everything into this specific bucket, right? So wouldn't that mean a hash table would be completely useless? And the answer is that we only care about a general, I guess situation. While we do have, while this may be the case, when we have large numbers, large input sets, it's only going to be likely that these input sets are going to be really distributed and sparse. And since we only care about n when it gets really large, we can safely assume that it's going to put these indexes into each bucket evenly. And although collisions may happen, this is pretty useful because we know for a fact that it's going to spread out evenly. So it's going to be inevitable that when the input size gets really big, there's going to be collisions. So one idea is how to handle collisions. One idea is really simple, is to do some kind of chaining. And basically this is when we have each bucket store a small linked list. So let's say we have a bucket here, and this is an array, and each index of the array store a small linked list, like a So let's simulate it. If we have k1 and k2 and Drew hash they put into a same bucket, we can simply add it, append it to the next, I guess, value. And then basically the lookup in the grand scheme of things, since we know that it's going to somehow evenly spread out through each bucket, the lookup iterating through this, I guess, simple linked list, since we know that this linked list is going to stay small, let's just say this time complexity of going through this is O of m. This is negligible.
Because there's never going to be a large amount of items in any given linked list.
Yeah, there's never going to be a large amount of item in any linked list in any bucket. So that's why chaining is really useful. And yeah, so in the grand scheme of things, if you have large input data, like this, collisions may happen, but our hash function is good enough that it makes it negligible.
It's one of those things where once I get it to a degree, I need to go practice it in a problem, and that'll really, once I do 5 or 6 problems with it, it'll really click. But no, it's like a very clever way to deal with using this data structure to solve a problem that would otherwise take way, way too long.
Yeah, it's O of 1 lookup, O of 1 adding, O of 1 removing, and you guys get that part, right?
Mm-hmm.